So right now what we're going to do is we're going to take a look at a thing called basic stretches, and they're horizontal. But first, we have to start with our basic graph, and our basic graph needs to basically just talk about all the different types of graphs that you'll see. Now, these are all polynomial graphs. Okay, so make sure you write down as polynomial. These are of the form y is equal to f of x, which is just x to the n. So when n is 1, this one here is linear. For n is 2, this is parabolic. So we call this a parabola or quadratic. This graph here is what we call a cubic function. Okay, now the cubic function always comes up and then swoops, comes up from the bottom and always swoops up when it's x cubed. When it's negative, it starts here and then does the opposite side. Okay, so now let's move on. When we take a look at this next graph, this is called a quartic function. D is called a quartic. Now, D is a quartic function, and it's it's a quartic because it looks like a parabola, but it has a fatter vertex. Now, this you've seen before. This next one, E, is called a inverse function. We call this the inverse of x. Just 1 over x, right? And the left side of the graph swoops down and then comes very close to the x-axis, but never crosses it and never touches the y-axis either. So we have something that looks like this for the other side, right? Now, when we have the negative, basically what would have happened is you would have had something like this or something like this. If we had negative 1 over x, it would have been that. Now, for this next problem, we have 1 over x squared. So x squared is just something like this, and you'll notice that the graph goes very, very close to the x-axis and then drastically goes straight up but never crosses the y-axis on either side. Okay? And that is 1 over x squared. Okay? So now, this next graph we've seen, you saw an example of that earlier. We called this the square root function. We call that the root function. Now, this is the cubed root function. This is called the cubed root function. That's something that looks like y is equal to the third root of x. And this last one is the third root of x squared. You'll never really see something like this in the real world. So I'm only showing you this right now because you might see one on your homework. So now we're going to talk about horizontal shrinks or stretches. So imagine we start with some arbitrary graph, y equals fx, okay? We can get the graph of y is equal to f of k x. So now what I'm going to do is I'm going to tell you what actually happens if k is bigger than 1 or k is between 0 and 1. So if k is greater than 1, then y equals fx has a horizontal shrink by 1 over k. So we literally just take the x values and multiply by 1 over k. That's all that happens. So now if k is less than 1 but greater than 0, this is what happens. Well, then we end up having for the second one, for k being less than 1 but greater than 0, y is going to be a horizontal stretch by a factor of k. So remember, if I have y is equal to f of kx, we have this. So here is our problem. So imagine I give you this function, y is equal to f of x. So now let's say that our graph started like this. Fx was some random looking graph. We'll start it in red. Start at 0, 0, and we'll go to say, let's go to 4 and 5. So this point here is 4 and 5. Okay. And then this point here is going to be, let's say 7. Nope. Let's make it 8, 0. So this red graph is y is equal to fx. Okay, so now in red. So in blue, imagine we want to go and see what y is equal to 2fx is. So we knew that this 2 was a vertical stretch of factor 2. So what we would do is we would take our y values and just stretch them by 2. So 0, 0 still stays. All right. But 4 stays the same, but the 5 gets stretched by a factor of 2. So it gets stretched by a factor of 2. So now our new point is 4, 10. Our next point is 8, 0. So 8, 0 still stays there, right? So our y value doesn't change. So now our y, our new graph is this blue one, which got stretched this way. So now, let's say we took our graph now and we were going to look at this. Y is equal to f of 1/2 x. So the 1/2 literally just multiplies all the x values by 2. It's a horizontal stretch by a factor of 2 because in this case, we said our y value was, it's a horizontal stretch by 1/2. So just take the 1/2. So take all the x values and divide by 1/2. Okay, which really means just multiplying by 2. So in this graph, this blue graph here was y is equal to 2f at x. Now this green graph is going to show what happens to all my x values. So my x's, and these are my x's that get changed. So my x's are going to be stretched by a factor of 2. So now for 8, 0, which was here, we're going to take the 8 and multiply by 2. So multiplying by 2, our 8 value becomes 16, 13, 14, 15, 16. So it's going to be 16, 0 for the first point. Now let's go back to our original function f of x. At this point here, 4, 5 was right here. So now our x value gets divided by 1/2, otherwise known as multiplying by 2. So what happens is the 4 in the 4, 5 becomes 8, 5. And then finally 0, 0 stays the same. So now there is our new graph. So that means that this is y is equal to f of 1/2 of x. So now, let's put a challenge here. What would happen if we graphed 2f of 1/2 x? So let's check out C. Y is equal to 2f of 1/2 of x. So the 2 in front, let's go and make this a nice different color. So the 2 in front stretches the y's, which is a vertical stretch by factor 2. Okay, so it's a vertical stretch of our y's by a factor of 2. But then on the inside here, our x's get stretched by a factor of 2. So stretched by a factor of 2. So if you see 1/2 inside our brackets, just flip it, and that's what happens. So we take our 2, we take our x's and multiply them by 2. So for the first one, so for the first point, 0, 0 still stays, okay, for this graph. Now, but now we have to look at what happens with the 4 and 5 from our red graph. So the 4 gets stretched by a factor of 2, so it goes to 8. But then its y value gets its x value gets stretched by a factor of 2, but then its y value also gets stretched by a factor of 2. Oh, would you look at that? There's our first point. So it's at 8, blah. Okay. Oops. Oh, yeah, 8, 10. Yeah, so there it is, 8 that. And then there is our first set of points that goes up to here. Now, the next point is 8, 0 from our original graph. So we get stretched by a factor of 2. So what happens is 8 becomes 16, but then 0 still stays 0. So now there's our last graph. And there we have it. First problem completed. So now imagine, instead of giving you some arbitrary function, right? What would happen if I started with y is equal to a real function, y is equal to the root of x, right? And remember from before, the square root of x looks something like this. Okay? So our graph is going to look something like this, right? Now I'm going to ask you a specific question about this problem, and you tell me if you can figure it out. So what I want you to do is it's going to be transformed into the following function. Y is equal to the square root of -2 times x plus 3. So I want you to describe the transformations and then also sketch it. All right, based on what we learned from before, you start with y is equal to the root of x. Then this is what we do for the rest of the problem. We identify each of the transformations. So we have y is equal to, going from left to right, we're going to have a -2. Oh my goodness, the square root of -x. Now, what this does is it flips our graph horizontally. -x flips our graph horizontally. So I'm actually going to show you that. So this flips our graph horizontally. So that negative x inside the bracket flips it. So let's go and graph our basic graph. So we got 0, 0, 1, 1, and then 4, 2, and then 9, 3. And then there we go. There's our graph, and that is y is equal to the root of x. So now the negative x aspect, I'm going to make that in black. So that's going to be here, and all the points are flipped in or mirrored in the y-axis. 1, 2, 3, 4, and then 9, 3. So now there is our new graph. And that is y is equal to negative root, sorry, not negative root of x, but the root of negative x. So now let's see what the 2 does. So y is equal to the square root of negative 2x. So I'm going to draw that in blue. And this graph basically factors. So here's what it is. This is a horizontal shrink. Let's call it a shrink by a factor of, instead of 2, it's like 1/2. So basically it takes all the x values and squishes them by 1/2. So 0, 0 still stays the same. Then instead of 1, 1, we're at 0.1 and there. And then the 4 gets pulled in. And then the 3, 3. The 9, 3 becomes 4.5, which is that spot there. So now our graph looks like that. So now we have y is equal to the square root of negative 2x. Now, the last portion of our graph is given by this. Y is equal to the square root of 2 of x plus 3. Please make sure that you add this extra little bracket here back up in our first part, in our first description of our graph. So now this is an x plus 3. So now I'm going to write this in purple. So in purple, here's what's happening. This is shifted left 3 spots. So when we shift it left 3, we take all our x's and move them over 3 spots. 1, 2, 3 from the blue graph. 1, 2, 3. So 0.5 plus 3 is going to be 3.5. Oops. Oh, I made a mistake here. This value of 2 needs to be shifted over right here. There we go. And then this 4.5 on the x's, add 3 to it, you're at 7.5. So 7.5 from this blue spot shifts all the way over this way. So now you're at 7.5. And that is our final graph. And that is y is equal to the square root of 2x plus 3. And we're done. So this is your homework. Before we do the homework, let's discuss the relationship of this. Example. This is important. Try to understand this. Okay. You're going to discuss the relationship between the graph of y equals fx and y is equal to f of the absolute value of x. Okay. So this is what you need to recall. When we go and graph our function, absolute value of x, it's equal to x for, that's if our x values were greater than or equal to 0. So essentially what's happening is for this black portion of the graph, that's what we got. So we have this portion of our graph. So it looks normal. It just looks like x, but for x greater than or equal to 0, that's what we have now. and it looks like negative x, and that's if x is less than 0. So essentially, we've got this half of our graph being represented, right? So what is happening? So here's the solution. So when x, oh boy, oh, let's erase that and write that properly. When x is greater than or equal to 0, absolute value of x inside our function fx is just equal to f of x. So if you think about it, what's happening is we're using just this form in our function. That's all, okay? So the graph stays the same. So graph is the same. So if my original graph was y is equal to x squared, it would just look like it originally did. Now, but, so when we have this, the x value being less than 0, f of the absolute value of x is really f of negative x. So remember, when we were graphing that absolute value function, it looks like negative x. So for x being less than 0, it looks like that. And this is a reflection in the y-axis. And that's all that is. Okay, and now your homework. So the homework for today's lesson is 37 EFGH. You're doing 40 through 44 and question number 46. And those pages will be posted in a few minutes.